Okay, welcome to this session. It's about the Pi on Wheels project. It's a do-it-yourself robot for teaching Java in the context of the Internet of Things. First of all, unfortunately, Gerrit Grunwald didn't make it because he had to leave earlier. But we'll do it anyway. So, okay. My name is Michael Hoffer. I work at the University of Frankfurt in Germany, and my research interests are basically visual programming concepts. But as a side project, I do also 3D printing and some IoT stuff. Gerrit and I thought about creating this little robot because it's very easy to build if you've got a printer. And I mean, printers are affordable for like schools and universities, so that children or students can build their own robot, and they can even modify the appearance of the robot and so on. So that is the goal for today, to explain what this robot does, how to build it, and how to program it. Okay. First, I'd like to give a short overview over the robot, and after that, we'll explain the Raspberry Pi and the GPIO pins and how we use that to control the motors. And after that, we will have a brief explanation of 3D printing and also designing the parts for the robot and coding the parts, actually, because who has actually seen the 3D printer in the Java Hub? Okay, quite a few. That's really great. And yeah, I also demonstrated a software there that we will use also here. And after that, we are going to show how to program the Pi on Wheels. We created a small API for that, and also how to use the XBee sensors. That's usually something that Gerrit does a lot to create sensor networks. Yeah. So let's start with the robot itself. Here are the parts that you need to build the robot. So first of all, of course, you need the Raspberry Pi itself, and then a few 3D printed parts, like this one here. It is the board holder for the Raspberry Pi. It looks like this. We printed that in the Java Hub. I've also got a white one. Looks like that. It's updated to the Raspberry Pi model B+. So we also have a version for Raspberry Pi B, so you can use either B or B+ if you like. And then we have some strange parts like this one, which is a battery holder. You can see it here. We use it to attach this mobile charging battery here. Usually used for smartphones, but it fits well into that. Then, of course, we need wheels, like this one here. And we also printed them. They look like this. And then we have some holders for servos and for the breadboard. And then we have the motors, the servo motors. Just two resistors for LEDs and infrared LEDs, like this one and this one. I've shown the battery already, and then you need a breadboard and a few cables. So that's pretty much it. So you don't need really very much to build the robot. Basically just a Raspberry Pi and a few other parts. So here's an example how you attach this mount to the Raspberry Pi, and underneath you see the sketch that I made to plan the robot parts. So here are the other parts, the breadboard holders here, battery holder, and then you see here the Raspberry Pi holder. So, and if you assemble it, then it looks like that. Basically just put the breadboard, battery, and everything together. I used this kind of breakout cable here for the Raspberry Pi. You don't have to use that. You can just use these male-female cables to connect. But this is also very nice if you're not decided which pins you'll use. So, okay. So how do we actually turn a servo into a motor? Because when you think about robot motors, there are different options like stepper motors, continuous rotating normal brush motors, or you can also use servo motors. A servo usually is limited in the angle. It's just for like steering something like a car, or it has actually a motor inside, and then a gear mechanism and a variable resistor to kind of estimate the angle of the servo. But they have the advantage that they are pretty cheap. So this is like this one. I got this one for like €5, maybe even €4, something like that. And it's very simple to turn it into a completely continuous rotating device. So you open the servo, and then you see here we have these gears here, which help a lot because it's quite strong. And then we have this variable resistor here to measure the angle. Okay, and you can't rotate it forever. It stops after like 200 and something degrees. And so you take apart the gears and everything. And here is also a little beast. If you don't take that out, then the gear will stop here. So you just remove that with a knife or something. First I missed it, and then I was wondering why it doesn't work, but this is quite important. And then here is the resistor again. And you just pull it back, basically, when it's in the middle position. This is one possibility. And the other one is that you could actually completely remove the resistor and replace it by two constant resistors to kind of simulate the middle position. Yeah, and this is like the mounting that we use for the servo, and then this is attached to the Raspberry Pi holder. So the servos run with pulse width modulation. And this is something that is quite easy to accomplish if you have hardware support for that. But the Raspberry Pi has only limited pins for that. So I think the B model had only one, and it was only increased with the B+. But we can also use ordinary GPIO pins. I'll explain that later, because we use a special service that hooks into the Linux kernel and simulates that for us. So here you see the pulse width. It's this one here. And then we have a period, like the frequency of the whole thing. And I mean, the proportions are not ideal here, because these are a lot longer. So you see frequency is like 20 milliseconds, and the pulse width is about 1 millisecond up to 0.2 milliseconds. And then you can control in which direction and at which speed the servo moves. So here you see the full circuit. We just use 3 of the GPIO pins from the Raspberry Pi, like I think it's pin 25, and then we have this, actually it was the pin 4, so I should have put it here, but it doesn't matter, because we have also the full schematics online and in a Fritzing schematics. Who knows Fritzing? It's a cool software for really painting the circuits and everything, and it's used a lot in IoT context. And then we have here the regular LED and an infrared LED. that we try to use for interacting with the XBee sensors later. So it's also, I mean, it's just a couple of minutes to build that actually. So do you have any questions about the hardware part, like how to assemble the robot or the electronics and servo thing? Okay, if not, then we move on to 3D printing. I mean, 3D printing is a really exciting thing, at least for me. I got my first printer like 1 year and a half ago, and it really changed the way I thought about and think about producing and prototyping things. Because, I mean, actually designing such a wheel is not so easy if you want to directly connect it to the servo and also the other parts. They have clicking mechanisms, and so it was not that easy for me to just manually do that. And with printing, it's no problem. I can tell the printer to just print like 10 wheels overnight, and other parts, it's really nice thing. Actually, I built this printer from a do-it-yourself kit. It's the first version of the Ultimaker printer, and you can assemble it in 1 up to 3 days, depending on your skills. Yeah, and this is the printer that I have in my office for just playing a bit and building these machines. So how does printing actually work? You've got a printing head that you can see here, and it has a nozzle, and you can also see it here. You see here this nozzle. It has a very small hole that you cannot see, I think, but it's very thin, like 0.4 millimeters. And here you see the nozzle isolated. And you heat the nozzle up, and then there is a plastic wire that goes into the nozzle, and then the plastic melts, and you get out very small, thin layers of plastic. And the printer will move around and put one layer on top of another. And the plastics that I used are basically PLA, which is a biodegradable plastic, and you can also print that kind of plastic in your office. It's no problem. And then there are other plastics like ABS, which are not so friendly. There are some, it doesn't smell that good, and it's not so healthy to print that in a living room or something. But you can do that as well. I mean, it is a bit better, more, doesn't break that fast and prints at little higher temperatures, but PLA is fine for building such a device, actually. So here is how printed parts look. If you carefully look, then you see all these layers it puts on top of each other. And there's a very, very cool thing about that, because I visited a friend just a few weeks ago, and he has an Electron Microscope, and we could really closely watch these parts. And I mean, these devices are very expensive, like hundreds of thousands of dollars. So here you see the Y, and you see it here with like this being 2 millimeters, and then we zoom in into also other parts around that Y. And you see here, these are 2 layers connected to each other. So I can see that there is a lot of structural stuff going on the micro level, and you see layers as well. And if you go closer, then actually the plastic starts to melt. So I cannot show you these pictures. Yeah, it was very cool, because you are then at the nano range and you see bubbling and stuff. And I first thought, okay, there's something crazy going on. I see atoms or something. But that was not quite it. It was really like the heat actually on the plastic. But if you zoom out, you don't see it anymore after that, because it's just so small. And it's really fun to watch that. Actually, I couldn't record a video of that, and I didn't dare to try it again because I could have broken the machine. And, yeah. So that's really fun. And 3D printing really, I mean, many people say something like, okay, you can print plastic, but what's the big deal actually? I mean, you can print bracelets and some funny figures, and we printed Dukes and stuff like that. But actually, I mean, it's a really huge improvement for prototyping things. And also that what we tried, and actually somebody created a fractal structure just a few days ago with the programs we showed there in the Java Hub. And I would love to try to print that, because such a fractal structure is not easy to build yourself, but it's very easy to print actually, because the printer doesn't care as long as you be in the limitations of the machine, then the printer doesn't care how complex the geometry actually is. And here's also one quite impressive mechanism. The special thing about that is that the joints here are just printed as they are. I mean, you have to take out one joint and then print it in a line, but actually the joints are printed as they are here. They are just a bit hard to move at the beginning, but the printer can handle that so that only very few connections are in between. It's quite loose, and then you can loosen them even further, and then you have really flexible stuff. And this is really hard to manufacture in any other way. And I even managed to print chainmail-like structures, like chainmail-like bracelets, and also gear mechanisms. Unfortunately, the gear was gone after 30 seconds when I showed it in the Java Hub, but so I can't show it here, because this is kind of quite the most impressive thing I printed, because it's a complete planetary gear mechanism that comes out of the printer completely assembled. And in school, I also attended to like workshops for building robots and ships, so like modeling stuff. And it was very expensive for me to actually get the parts, like special bolts and nuts, and get that assembled. And now it's really, really cheap to accomplish that. So I think this is a huge step forward, even if we in the consumer market can only print plastic at the moment and not something like metal or so. But still, I mean, metal printing is around for quite a while. And there are even people who like to use this for a kind of molding. Yeah? This one was a do-it-yourself kit. It sells for like €1,000, and it has the advantage over the one that we showed here, that you can improve it for dual printing. You can print even dual materials, like this traffic cone. I mean, you have dual extrusion, just 2 wires of plastic, different colored, and you can even do it like one water dissolvable and one water resistant, and then you can even break the limitations, like printing big overhangs, because the printer you saw in the Java Hub, when you would like to print something like 90 degrees, it would just fall down. But with water dissolvable material, you can just print up support structures and then print this 90-degree angle, like big bridges and so on, and then you put it into water, and then after several hours it's just gone. I mean, you can also do that if you just print it with ordinary plastic, but then you have to remove the support structures yourself. And here's also another example. I have I started to build a drone, actually, a 3D printable drone. And this is one arm for the drone. And inside there is a very fractal-like structure with a lot of air in it, but still very stable. And it's also very difficult to design any other way than just use printing, at least at home. And I built it like a bird's bone or something, just with some spaces and holes for cables and engines. And of course, you can also print stuff like a holder for the leap motion, so just a protection case for that, and things like that. So it's really fun. So the only problem we have not discussed so far is how do we create the geometries, right? I mean, it's easy to imagine something really cool, but then getting that as a real 3D object on the computer is not so easy. There are some options like professional CAD/CAM applications that you can use. You can even use Blender for that, which is open source, or OpenSCAD, which is also a script-based language for 3D modeling. Or you can use the new JCSG and JavaFXScad, and it's all done in Java. Yeah? So the problem with OpenSCAD for me, I mean, it's a very powerful tool. I used it a lot, and I'm really grateful that the developers did that. But the problem with it, the scripting language is quite limited. You don't have any editor support or like even variable array length or lists or some other collection types. And also, I didn't like the license. So everything you see here is under BSD license. You can do it for whatever you like. Just grab the code and do your own stuff with it. And it would be nice if you just say what you do with it. But there is actually no limitation. Because I think then if you want to provide stuff for teaching and for learning, you should give the users the ability to do anything with it, actually. So how does JCSG work? I mean, you have to think about how do you actually express the geometry. I mean, if you use JavaFX 3D, for example, you have these 3D triangle meshes, and basically you could just put in all the vertices manually and then assemble the mesh. But this is really complicated for something like this, or the drone arm or something like that. So we have to come up with a different solution. And this is something called a constructive solid geometry. This is a type of algorithms. And the operations that are supported are union. So we use these two circles, and we can union them into that object here. We can difference them, so we can cut out parts of a circle or a sphere or anything else. We can do intersection, so only the intersection remains after applying that operation, and we can also do a hull operation, like wrapping two objects. So the union operation. Here we see some source code, how that works in JCSG, and we just said we have a cube. And so here is the cube. And if I remove the comments from there, I get a nice sphere. And what we can do now with it is we can create the union. Okay? And there are also some other examples like this. We can move the sphere to somewhere else, and then we get this geometry. And the special thing is the intersecting polygons inside these two objects are removed. Okay? So it's completely just has one outline. So that's the basic idea of the algorithm. The same with difference. So we can just cut a hole into that cube. It looks pretty nice, I think, even though it's not so easy to print, actually. So we, again, create a cube, a sphere, and then we compute the difference between cube and sphere. So it's really easy and approachable, even if you don't know that much about like CAD operations. And here we just move the sphere a bit, and we get that geometry. And what you can also do is you can transform, like translate, rotate, and scale objects, which helps you with something like this. And then there is intersection, which is pretty cool as well, because you can have these like rounded cubes in a way. So we have a mix between the sphere and the cube. Another example, like this. Again, here we just have basically the intersect operation, and in this case, the transform. Okay. Yeah, of course you can. So, good question. So we should be able to say something like this. It's a bit smoother, and you can even smooth it further.
So is that just subdividing?
Yeah, it's subdividing. I know it's. I mean, when it creates the sphere, I mean, really, when it creates the primitive geometry, because actually it's a geometric object, but we translate that to like polygons in the first step, and this is what it does here. So 16.8 is what we used here, and I mean, you can keep that variable. I mean, you just have some variables in your code, and then you can change the resolution afterwards. Because if you create complex geometries, it takes some time if you have high resolution. Okay, and here is the hull version, which is also very interesting because it's just, you can imagine some plastic bag around the cube and the sphere. So like it first does the union of sphere and cube, like in the very beginning. And so, yeah, I can even change it more into a ball, actually, like that. We use this also a lot. Do something like that here. And can print pills. This is just using two spheres and then wrapping them by using the hull operation. And I think the API is quite approachable. I mean, it's not very difficult to get used to it. And I try to keep it that way that you can use like auto-completion in NetBeans, and it always tells you what you can do, basically. We also have JavaDoc for that. Okay, so now what about the software stack? We've got a server running on the Raspberry Pi. We have an API that you can use to control the robot from a client, and we do that with XML RPC at the moment. And yeah, then we have a very small IDE. It's a JavaFX-based where you can connect to the robot. You can create the geometries like I showed you on the previous slides, and you can also interact with it and program it from Groovy. So here, the JCSG is completely integrated into that, and you get all the source code after the session. So what I did to actually install that stuff, I just took the ordinary Raspberry Noob image, put it on the micro SD card, and then I installed the server that I wrote, and on the client, of course, we have to have the IDE. So how to install the server? So first, apologies for that the link is not yet working because I had problems with internet previously because I was not here in Hilton, but I will upload it as soon as I can. So everything, as I said, is open source. You get all the source code, and I also give you the precompiled server application for the Raspberry Pi. This is also because it incorporates some services that, in addition to the Java code, but everything is inside there, and you basically just run the Pi on Wheels server script, and then you're up and running. What you can also do is you can use the rc.local file on the Raspberry Pi and just add the Pi on Wheels server there, and then just reboot the Pi, and it will start on every reboot. So here is the IDE. So we have just a connection screen. Actually, it doesn't do anything because it scans for Raspberry Pis in the network where it's currently connected to. So you don't have to specify any IP addresses or so. And if you have more than one robot, it will just connect to more than one robot. Then we can interact with it. We can program the robot, and here we have a very nice control that I will show you later. Gerrit has created that one. It's a really fun, locating control, radar control. And here is the design application. So maybe I show that now. So now the Raspberry Pi connects to the hotspot that I created with my smartphone. And this LED that you also saw in the schematics is used to indicate the state. Like when it's booted up, it should blink. I just leave it here for now so that you can see it, because if I put it on the floor, probably you have difficulties to see the robot. So you see now the Raspberry Pi is blinking. So, and here we are connected. Okay, we get this nice connection screen, and we are talking to the robot. So now the API, okay, I just show it here. I don't know if you can see that actually. The font size, is it too small? Okay, it's fine. Yeah. So I think it just crashed. So let me try again. Sorry. So what we can try is we can move the robot forward for like 3 seconds. And if I run that, just keep it. And you see we have a small dot that moves. So even if you turn off the robot, you will see where it would move. So now let's try it on the floor. And we try that, and it should. Oh, it's stuck. Okay. Yeah. Let's try again here. So that's how it works. And as I said, if you connect more than one robot, then it will just distribute the commands to all of them at once. So we have API for actually moving the robot, and also for letting the LED blink a little, and also for changing the state of the infrared LED. Under the hood, for the pulse width modulation, we use the Pi Blaster daemon, which is incorporated into the jar file, so you don't have to do anything. And it will talk to it because it creates a Linux device, and then you can specify the pulse width. And just let me briefly show you the implementation here. This is the server application, and here I created a pulse width modulation class, and you can specify the min value and max value and sender values and which GPIO number it should choose. And the cool thing is you can actually use any GPIO pin for that, and you won't do software pulse width modulation, which is usually used if you want to do it with regular GPIO pins, but it uses kind of a hack actually in this daemon, so that it can do pulse width modulation without using the CPU too much. So it's quite precise. And the servo can turn, it can stop. That's basically it. And the LED, it can you can set the brightness, and you can also release the LED after usage, or it can blink with certain frequencies and stuff like that, so it can really communicate back from the robot. And you can do that from this IDE. What you could also do is you could actually, I don't know. I will show that inferred stuff later when we come to the XBees. So what we did here is made for teaching, right? This is why we created this small IDE, so you should take that and use it for teaching kids or students or whoever you like, because you can learn programming in there. And I don't know if you were in my previous session yesterday. It was about visual programming, and we'll bring that all together so that you can also use the visual programming IDE for that robot, but it's not yet done. But it relies on Groovy in this case here, the text-based version, and also the IDE relies on Groovy, so it's not difficult to bring those two together. So here is the design software. You can just type any kind of code you like, and of course we have prepared examples like the board mount, which looks like this. And you see we have predefined classes as well, which you see here. You can just create a class that does all the polygons for us, and then you can use that and combine that. Let's see, the wheel. It's that one. And you can also save that directly as STL file for the printer, or as PNG, like just a snapshot as I did for the slides actually. And you can save the script files here. We have a special ending like JavaFXScad, or you can just save it as Groovy. And we actually also did that with interacting here with the API. It's just called Pi on Wheel script, or also Groovy. So that's the basic soft and hardware interaction. You saw the API and this IDE. Any questions about that part? Yeah.
I'd like to know about the 3D printing I forgot to ask before. What kind of plastic wire you're using for printing?
I mean, type of material?
Yes.
It's called PLA. It's biodegradable plastic. It melts at like just below 200 degrees or something. I don't know exactly, but about that. And all these parts are made of that plastic. And there are other plastics as well, like flexible PLAs that you can use for bracelet and stuff. And then this water dissolvable that I talked about, and also ABS.
And how do you combine during the printing process different types of materials?
I mean, as I've shown here with the cone, you just have two extruder heads. And then you print the white one, and then the gray one, and then again the white one, just by switching the nozzles, basically. So you cannot really mix the colors, like I want 90% gray and just 10% white or something.
But that switching can be controlled through program, right?
Yeah. I mean, if you do it with the JCSG, then you just create, like when you saw this cube example. We just go back to, no, actually it's difference, like this one. You could also use everything that is a whole now. You can just do apply the difference the other way around, and then you use both, one for color one, and then for the second color you use the other one. So I could have done something like sphere difference cube. You know, this is this one here. And by combining both of them, then you get a dual color print. Oh, yeah. No, actually not difference here, so it's intersect actually, because this one, I mean, it looks cool, but it won't print. Yes, this is the intersection, okay, and the other one was the other color. And then you just feed both into the printer software, and when you do that, then you have to make sure that you select both and say dual color print, and it will merge that back again, because the STL file format in its original form does not have support for multiple colors. But that's the way I created this cone, so it's fairly easy actually. Especially if you mix different materials like flexible ones and non-flexible ones, this is really fun because you have flexible parts and non-flexible parts, and it's really nice for bracelets and stuff like that. Yeah. Other questions?
Can you get the IDE somewhere?
Yes, as I said earlier, everything is completely open source under BSD license. As much as I can. Some parts might be under LGPL, but still usable for basically anything you like. But I like BSD most for teaching and stuff, because you should be able to do anything you like with it. If you have a great idea, then just do it. And I didn't have internet earlier, so I will upload the server, a precompiled version of the server later. But actually, everything you saw in the slides, like the code examples, which is also just a JavaFX program, is already online, and the other one will be published today, and just on GitHub. And if you visit my web page, I can give you a card later on, and then you just go and download. And also, if you read the session description, then it will be shown there as well. Yeah. So, basically we covered the Pi on Wheels API, and then Gerrit and I thought about adding support for these XBee modules. Who knows them? Okay, a few. These are small devices running at 2.4 gigahertz and like 2 milliwatt, and they have an indoor range for like 40 meters. And actually, we got the XBee Pro in this case, so it has an extended range. I don't know exactly the range, but it's more than that. And it has outdoor range here for the normal XBees is 120 meter. And we run it at 3.6 volt, and it has a impressive operation range from -40 to up to 85 degrees Celsius. So they have different mesh or like connection types, network types, and they are programmable, which is really cool. It's kind of a small controller in there. And they also have very small wake-up time. This is very fast. If you connect them, they are just up and running. As you saw earlier with the Pi, this is not the case. It takes like seconds up to a minute or so to boot. And it has its own standard for the remote thing. Here are the connectors. You can connect like VCC and GND. You have digital pins, even pulse width modulation pins, and you also have analog pins. This is really nice because you can read analog values as well. This is the setup that we use for those sensors. So we have an infrared receiver on them, and you could use that, for example, for interactive even further with the robot. So it has to drive to a certain point, and then you move around and stuff like that. or you could also send commands explicitly from the computer and then hand it over to the Pi, whatever you like. And these small devices are also very easy to set up. I mean, you just need a small battery. It's a battery that runs at 3.6 volt, a few cables, breadboard, and then here a breakout board for the XBee, one resistor, and an infrared receiver. That's everything you need for that setup. It costs about €25, depending on where you get them. So now about the network topologies. First, there is the mesh topology that has a really mesh-like structure. The nodes are communicating to each other, and it's good for wide-range networks because if you try, for example, to communicate from this one to that one, this is the distance that matters, right, between two nodes. And the actual path through the network will be discovered by the devices themselves. So it has the advantage of being self-healing. So if a node doesn't work anymore, then you still have, if you have another path from one node to another, then it still works. And it has, as I already mentioned, a wide range. And yeah, the problem, however, is that it's very complex to set up, and you broadcast all the time, so therefore you have higher power consumption. So that's why we use the star topology. So we have one coordinator, it's this one, connected to the laptop, and then we communicate with all the nodes. So we have not such a big range, but in our case, this is no problem. It is very easy to set up. I mean, besides the fact that setting up these devices is not always that easy because sometimes they just break. I mean, because I started developing for those just 2 weeks ago, and when Gerrit gave me those, and I started playing with them, and I said, okay, I broke them all because the software tells me that they don't respond and I have to rewrite the firmware and everything. But then he said, yeah, sure, that's quite common, so you have to try 10 times and then it works. And that's exactly how I set them up. But on the other hand, if you set them up once, then they just run forever. So the star topology has the advantage of having low power consumptions because each node knows that it only has to communicate to the coordinator, and this one here is wired via USB, so it doesn't matter that much. It's easier to maintain. A problem is maybe that you have a short range, or that the coordinator is the bottleneck if you have many nodes. But in our case, this is not a limitation. And of course, you don't have interaction between nodes. But yeah, for this case, this is the ideal setup. So, no, that was too fast. We want to demonstrate now the feature here. So, as the robot doesn't drive that well, I just show it like that. But I'd like you to see these LEDs, and if I connect or I hold the sensor near an LED, okay, it doesn't yet work. Don't know, maybe the battery is broken. No, just let me try to restart that. That. So actually there's native code in it, so we just blame the native code for having it not working. That's really bad because it's actually so much fun to watch that. So then I say that we are open for questions. I try to fix that while you ask questions. And also for the first 3 questions, I'm giving away these if you have Raspberry Pis. So we have 3 Raspberry Pi holders. So yeah, a question here. What?
No, it's okay. I will check that.
Yeah. Yeah.
Noticing it didn't really move very well on carpet. Would just a small passive wheel instead of a plastic anchor?
It would actually, and what we thought about is having like a small ball inside, you know, even like a metal ball inside, and you could click it and then it could move freely. This is what we thought about, but I have to redesign that for that. So because there.
Use a slightly larger scale.
Yeah, this is also an option. Yeah. Yeah. You get one?
Thank you.
You're welcome. Next one. No further. Yeah.
Is there a place we can buy the parts? We can purchase the parts?
Excuse me?
Is there a place online we can purchase the parts?
You mean the electronics?
No, the printed, the 3D printed.
I mean, of course, there are services that sell that online. I think they are not that cheap. So if you plan to use that for education, really, and let students or kids play with 3D printing and designing, then you should probably consider buying a printer, because then it's easier. But if you only want to print one part, or like just for seeing how that actually works, then it might be sufficient to just order that online. There are several services. I mean, I don't know where you're located. Just check online. And also there is a web page called Thingiverse, and there you will get pretty much anything you like. I mean, even if I designed everything myself here and I uploaded it also to Thingiverse, but to be honest, everything you need, I mean, like for drones and for robots, and there's so many parts that I've already designed there. What I'd like to encourage you is to use the JCSG and upload your own designs and the source code to Thingiverse, because what I don't like about the OpenSCAD, it's a very restrictive GPL license, so it's very difficult if you play with stuff that is not under GPL, and then sometimes people refuse, or companies are not so happy with GPL. Of course, things should be open, but I think BSD is a better option for that. Yeah.
You mentioned that you're using Pi Blaster for your modulation. How are you interfacing that from Java?
So I came up with a solution to actually integrating that into the jar file. Like so. We have the Pi Blaster binary inside the jar file as resource. And now let's see, pulse width modulation device. So I have a file writer to the device, the Pi Blaster device. And I can write a pulse width modulation command. I mean, this is all private, so not exposed. And to start the Pi Blaster, I get the URL to the resource. I just copy the file to like something like temp Pi Blaster, make it executable, and run it. So it's really easy, because a Java developer will not notice that there is the Pi Blaster behind. So I don't want you to install special packages, recompiling your kernel or something like that. I mean, there's also this Servo Blaster, which is specifically made for servos, but you have to recompile, use a kernel module, and I like that one much better, because it's broader for not only servos, but also LEDs and stuff. And integrating that into a jar file is really easy. And it's at the moment made for the Pi, but one could also extend that to support other boards as well. Yeah.
How do you configure the runtime performance of the robot? Have you ever
Which performance?
Real time.
The real-time performance. I mean, no. I mean, real-time performance means this is just a robot that moves around and is for teaching stuff. So I didn't have any performance measures really. So yeah. So if you have further recommendations or your own ideas, I mean, I would also like to improve that, to also support other robot models, but this is just the basic one that we just designed now. The focus is, of course, to keep that very simple so that it's easy for people to build that one. Of course, not every school or university has a 3D printer, but I mean, the technology is moving, and I think it will be in almost any, at least university, in just a couple of years. Yeah. So I'll try to set them up. If you are interested, then just stay here for a few minutes. And yeah, then thanks a lot for attending.